What do you think? Don't be shy, right? You know, ask questions. You are here to study, right? I know you don't know anything, right? Don't pretend. You know. Anything? Any? Okay. Okay. Any? Okay. Again, don't be shy. Okay. Don't be shy. You know, ask questions. Okay. I like this class to be interactive, so you know, please don't be shy. Okay, let's get started. So we are talking about interrupt and exception in computer. You know? That is super important mechanism, right? Exception, interrupts are happening inside the computer system all the time. Okay? So for computer system to work properly, you should understand. To understand interrupt, you have to understand interrupt and exception for computer system operation. So interrupt and exception. And interrupt can be divided into two categories, right? Hardware interrupt and software interrupt. Hardware interrupt are typically generated from I/O devices, right? Keyboard, mouse, timer, GPIO, you name it, right? I/O devices. It is going from I/O devices. And software interrupt, it is provided as an instruction, CPU instruction. Okay? So we have SVC, Supervisor Call Instruction in ARM CPU. So Intel has INT x86, right? INT instruction. RISC-V has Environment Call Instruction, E-Call Instruction. So every CPU is providing one software interrupt instruction. So it is very simple, right? You put that instruction in your code, then CPU executes it, then software interrupt is generated. It is that simple. And exception, I gave you one good example, right? So undefined instruction is one good example of exception. We will talk about some more examples of exceptions later on, but undefined instruction, that is good example, right? CPU read instruction, but don't know what to do because that is not defined by CPU architect. ARM is not providing that specific instruction. Okay. So in the decoding stage, right? Think about 5-stage pipeline in CPU: instruction fetch, decoding, execution, memory access, right there. Right? So after reading memory, after reading instruction, CPU is interpreting, right? Fetch, decoding, execution, memory access, right there. This one is very classic 5-stage pipeline. Right? So after reading instruction, the CPU is trying to interpret the machine code, the decoding stage, and then actual execution. Right? In the decoding stage, CPU will take a look at operation code. But if the instruction the instruction CPU fetched does not have a legal operation code, then that is undefined exception. CPU does not know what to do. Right? So last time we were talking about this one. So we were in the middle of talking about supervisor call, software interrupt. And interrupt happens, what you have to do is this one. So interrupt happens, what you want to do is, CPU is executing your application program in user mode. Then you want to execute special program for that interrupt. That is called interrupt service routine. Right? So here, your application program, you have special program called interrupt service routine for that particular interrupt. For SVC, you want to execute the ISR. Right? So you stop executing your program, then branch it to ISR, then after that you resume, right, from interrupted place. So that is the big picture. So what you want to do is you want to execute ISR, right? ISR. Then the detailed step before you execute ISR, this detailed step that is defined by specific CPU. ARM architect defining a detailed step. Intel architect defines detailed step. Right? RISC-V architect, the CPU, defining that detailed step. So your job is to study, what kind of steps you have to take to run that code. Right? So that is what we have studied last time, the detailed step. So during this transition, hardware is doing this operation, right? So what you want to do is basically you want to save the state. You want to preserve the state of your application program. This is important, right? You want to preserve the state. Okay. Then after you resume, then you start from that saved state. So from application point of view, it is like nothing happened. Even though actually interrupt is generated, but from your application program point of view, it's like nothing happened, right? CPU kept executing your program beginning to the end. Right? So nothing happened, right? So that is what you want to achieve. So what kind of state then you want to preserve, right? So you want to preserve the context, CPU context. I think you have heard about the context switching in operating system code. What is CPU context? General purpose register. In case of ARM, R02, R12, I think, because if you look at this register map, it is R02, R12, right? These are common regardless of operating mode. Usual mode, you are using that 13, right? R02, R12, 13 registers. And supervisor mode, you are using you are accessing same 13 registers, right? And IRQ mode, you are using that same R02, R12. Right? So IRQ mode, you have physically separate R13 and R14. Stack pointer and link register. Right? Supervisor mode, you have separate here R13, stack pointer, and link register. So what you want to do is you want to save R02, R12, because you have separate R13, R14 in each operating mode. Right? And in addition to this, you have to save CPSR, current program status register. Those are information you want to save. Okay. So then during this transition, some essential operation is done by hardware. That is essential operation. Hardware must do. Right? I spent a lot of time, right, explaining this one. So that is done. That is done by hardware. Right? And the remaining job should be done by software. Right? So it is essentially saving CPSR to SPSR. CPSR to SPSR. So in ISR, what you have to do is at the beginning here, you have to push. You have to push R02, R12. And before you return, you have to pop R02, right? Push, pop, right? R02, R12. Okay. So that is this one. So during this transition, hardware is doing some operation, right? In the previous slide, right? CPSR to SPSR and some more, right? Then refer to program counter will be changed to one of these value, depending on exception type or interrupt type. Okay? So then you can make that transition. You can branch it to actual ISR. So what you have to do in software is push and pop, and in between actual operation you should do, like, for that interrupt. Let me show you that demo. So any question so far? Okay, let me show you the demo, right? So I promised you to explain this code again. I forgot to turn on the board. Let me go to my office and turn on that board. Okay, so this is interrupt vector table or exception vector table, right? I created. So from now on, we are going to use that interrupt vector table. How come? Because we are setting a vector base register using MCR instruction. Okay, so after executing this instruction, MCR, then CPU know, okay, this is an interrupt vector table. Okay, we are going to use. Then let me download it. Show you. Software. Okay, vector base register setting. So check out this register. It is displaying, it is dumping not only general purpose register, but system registers like VBAR. Okay, so check out this MP4. Then I think so P15 means coprocessor 15. So scroll it down. Okay, here CP coprocessor 15. Okay. Then I think C12. This is the one. C12. Then this VBAR is here. Vector base register. Okay. So using this window, this pane, you can check out a VBAR. VBAR is initially set to 1 5 zeros. Right? Someone already set VBAR to 1 5 zeros. Right? Then we are going to change that VBAR to this one. What is that? CSD table. Check out compiled binary. Design. Help. Search. Control C. Search. Okay. So according to this symbol table, compiler created, our interrupt vector table starts from this location 5A0. 1 2 zeros 5A0. Sorry, try to remember 5A0, right? 5A0. So if I press F5, okay. So press F5 one more time, then VBAR register. This one will be changed to 1 2 0 2 zeros, 580, I think, right? 5. See? 1 2 zeros, 580. Okay, VBAR, vector base register. Okay, so don't worry about this barrier, instruction. Don't worry too much about it. Okay. Don't worry about this. Then MRS, MSR, using these 1 2 3 4 5 instructions, we want to change operating mode to supervisor mode, right? So ARM is providing 9 different operating mode, right? And we want to change that to 1.3. 1.3 is supervisor mode. The reason is we want to set up this stack pointer. This here. Change that to supervisor mode, right? Change it to supervisor mode, and we want to initialize this stack pointer because we want to use separate stack for supervisor mode. So at the booting sequence, if you turn on smartphone has ARM CPU, right? And JetBoard has also ARM CPU. So in the booting process, turn on the system. In the booting process, the first thing you should do is set up this stack pointer. Stack pointer in user mode, stack pointer in supervisor mode, stack pointer in abort mode, right? Change operating mode and set up the stack pointer. That is first thing you have to do. Initialize the stack pointer. That is in the booting process. Okay, so you have to reserve, right? Going back to our code. So going back to supervisor mode stack, right? That is created here. Okay, I reserved 1 kilobyte in memory. Okay, 1 kilobyte, right? So what we have to do is memory, right? So you have all the power, right? There is no operating system. You have to do everything manually yourself, right? You are allocating, okay, this 1 kilobyte. Okay, I'm going to use this one for stack for supervisor mode stack. Okay, and I'm going to use this 1 kilobyte for IRQ mode stack. Okay, I'm going to use this 1 kilobyte FIQ mode stack and so on. So you have to reserve some memory area, okay, as a stack for each operating mode. Then set up stack pointer starting from 0. By default, we are using full descending stack, full descending, right? Full descending. So address is incrementing like this, then stack pointer. So SVC, SP, so R13 essentially, right? R13 should be set to 1 byte above that. Okay, and IRQ mode. R13, right? Same R13, but in IRQ mode, right? That should be set to 1 byte above that actual stack. Full descending, right? Full descending. Remember when you discuss LDM, load multiple, store multiple operation, there are several addressing modes, right? For stack. Full descending, full ascending, empty descending, empty ascending. By default, we are using full descending. What does that mean? What does that mean? The location stack pointer is pointing is already full. Full, right? Full and descending. Okay. The location stack pointer is pointing already occupied. So to push new data, you have to decrement. So okay, so that is the one. Okay, so that is look at SVC stack top, right? So SVC stack top. Okay. And then there are two options you can use to change operating mode. One is using MSR, right? General purpose register to as status register, and the other is CPS instruction, change processor state. This one is shortcut, right? This one is more convenient. So I don't want to use this sequence, right? So why do you want to use 5 different instructions given that one instruction can do the same operation. Right? I don't want to use 5 different operations, just this one. Okay? So this instruction is doing what? Changing operating mode to user mode. Okay? According to this one, user mode, right? So M field is 1 4 zeros, then there is user mode. Right? So 1 4 zeros. Change it to 1 4 zeros. Then in addition, you can do, what is that? Interrupt enable. So in CPSR register, you have A field, I field, F field. Okay. So you can set or clear AIF with CPS instruction. Right? So interrupt enable means it is clearing AIF. Clear means 0. Okay. So what is the implication? If I bit is 0, okay, then CPU is going to take interrupt. Right? So ARM CPU, you have IRQ, FIQ. Two input, 2 interrupt input, right? And CPSR, you have I bit and F bit. If you set I bit to 1, that means what? You are not going to take interrupt, even though your interrupt line is raised. You press the keyboard, you move your mouse, okay? The line got raised. So CPU say, okay, I'm busy. If you set this one to 1, I'm busy. I'm not going to take interrupt. If you set this one to 0, then that means interrupt is enabled. CPSIE, interrupt enable. I want to enable what? AIF. That means clear this bit to 0. Okay. So interrupt enable clear. Okay, interrupt enable clear is 3 bits to 0. Okay. Now CPU will take interrupt. Okay. At the same time, change operating mode to user mode. Okay. So you are in now user mode, then SVC, software interrupt instruction, is executed, right? So let me execute this. So probably expand this, right? Here. So mode bit is 1F. 1F means what? 1F means system mode, right? 1F means system mode. Someone changed operating mode to 1F. Okay, someone. Okay, I think Xilinx putting code. Okay, I'll show you. Okay, so after this demo. So before this main, you know, some code got executed, and you got this point, right? You got this main, right? Someone cook up some program, and ARM CPU already executed that program and jump into this main and stay here. So you are in system mode. So let me change it to here. If I press F5, then M mode bit will be changed to 13. 13. 13. Okay. So supervisor mode. And this one is changing operating mode to user mode, 10. Then N AIF, these 3 will be clear to 0. Right? These 3 will be clear to 0. Yes. Okay. 6, 10 mode bit and AIF, right? All 0. Okay. So now CPU is going to take interrupt. Okay. So supervisor call. Then what should happen? Then according to that protocol, right? Architect defined like this one. Supervisor call. Then this operation will be done. Okay. Then program counter will be changed to what? PC will be changed to 08 plus VR. From this base location, plus 8, offset 8. Right? In case of software interrupt, that means from this location V bar, so 0, 4, 8. Right? So that instruction will be executed. Let me press F5. So that instruction. Okay. So interrupt vector table. So this is branch instruction, right? So just call branch to that label CSB software interrupt. That is here. Okay. So first thing you are doing is this one. Right? So this one you are here. So you executed SVC ISR, then your second, right? It's 2. So you are at this point, right? Push CPU context. Right? Using software, using STM, store multiple instruction, you are pushing CPU context to the stack. Right? So stack pointer R13. Stack pointer is what? Stack pointer let me write down. Stack pointer what? 1 2 zeros. 1 2 zeros. E10. 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 So that is a stack pointer. Stack pointer, then you want to push. And full descending. So you want to push R0. So these R0 to R12. R0 to R12 to the stack, right? Let me open memory. Remove. Okay, add. E10, right? Okay, so E10, then right, full descending, right? So full descending means so you are pushing 13 registers. Okay, so full descending. So address is decrementing like this: E10, E00, EF0, decrementing like this, right? So what do you expect if I press F5? E10, right? Somewhere here, right? Somewhere here, right? Somewhere here will be populated with R0 to R12. 13 registers, right? Full descending, right? So those values R0 to R12, those will be pushed to here. Very crowded. Okay, stack pointer, let me check. Stack pointer E10. Okay, so let me press F5. E10. Is it? No? DDC. 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 I think it's correct, right? E10. Do you see any problem? Did I do something wrong? DDC. DDC. Right now, new step pointer is DDC somewhere here, right? DDC. I don't know. I don't know. You can check out. Okay. Probably I did something wrong. I don't know. Okay. So then next code is doing turn on LEDs, right? Turn on these LEDs. Right? Turn on these LED. So okay. Then pop, right? Pop the data you saved. Okay. Pop the data you saved into R0 to R12, right? I don't know, it's very crowded. Okay, let me remove this. Then R0 to R12 will be loaded with the data you saved here. So, okay, so new data, okay, and no change in R3 to R12, R3 to R12, because we haven't touched it. We haven't touched it. R3 to R12 in this main, right? In this main routine. Then you are returning back. You are returning back to the interrupted place using move S. So you have to be careful. If the destination is program counter, then you have S suffix. Then it has a special meaning, right? SPSR. SPSR will be copied to CPSR. Right? You copy it. Okay? Opposite operation. SP does. You saved CPSR. Right? SPSR. So here you have to do opposite operation. SPSR to CPSR. So that is the meaning. S and destination is program counter. Then so you are here. Okay. Then forever loop, right? So you are generating another software interrupt. So that means you are branching to interrupt vector table. Okay. Then push operation toggle LED. Okay. Pop, return back to the interrupted place. Keep doing this operation. Okay. Okay. Any question? Okay. One thing before finishing this demo. What if I comment out this one like this? This. What if I comment this out? That means we are not going to use that interrupt vector table, right? Okay. So let me execute then. Then CPU will use other interrupt vector table which Xilinx is created. Okay. So V bar register, if you remember, V bar was set to 1 5 zeros. Okay, at the beginning. Then we changed V bar to 580, right? So if you comment out this, then CPU will use that previous interrupt vector table 150 location, 150 location. So let me execute this. It's done. Okay. Then execute this until this point. Then now if I press F5, then V bar, right? Check out V bar. V bar is 1 5 zeros. Okay. Then so that is the, look at this. This is not our code, right? Someone created that vector table. The Xilinx, this chip provider, Xilinx, the company called Xilinx is providing this chip, and they are also providing this the booting code. This booting. ASM vector dot S. Okay. So V bar register initially set to this the symbol. Okay. So it is now referring to this vector table trying to execute SVC handler. Right? Press F5. So that is the handler, right? So it is saving some registers. Okay. So now you are free to use because you saved R0 to R3, R12, and link register. You are free to use R3, R0, and some other registers. Okay. And that is located if I turn off. That file is located here, ASM vector.s. ASM vector located here. Platform hardware project. Okay. Standalone, then ASM vector. So if you are interested, probably you want to follow, probably you try to follow this booting code. It is written by professional. So so Xilinx, the professional in Xilinx. So you want to analyze that booting code to see what kind of operation is done in the booting sequence. Okay. It's a good reference, right? Check out this code if you are interested. Okay, any question? So now we are done. We are done with this one. Okay. Software interrupt. Okay. So now we are going to talk about the simple one first. This one is a little complicated. Hardware interrupt. So let's talk about this one. Okay. Exception. Okay. Exception. This one. Did we talk about this slide last time? No? Okay. So this one is talking about what? When some event happens, some interrupt happens, some exception happens, right? FIQ, IRQ. Interrupt happens. Hardware will set in case of FIQ. So here, right? During this transition, I bit, right, or F bit will be set to 1. That means what? Again, that means CPU will block while processing interrupt. If you say, okay, I'm busy processing interrupt. I'm not going to take any additional interrupt. That is the meaning, right? I bit to 1, F bit to 1. That means I'm not going to take IRQ, okay, from this input. I'm not going to take FIQ, okay, interrupt. So depending on interrupt or exception types, look at this. If FIQ interrupt happens, if this line got based, then CPU will set I bit to 1. Okay. CPU will set I bit to 1 and F2 bit to 1. Okay. This one is called the fast interrupt. We will talk about that. Fast interrupt and normal interrupt. This one has higher priority than this one. What do you mean by that? Higher priority means if 2 events happen at the same time, let's say you have keyboard is connected. Okay? Keyboard is connected, okay? And here timer. Simple example. Timer is connected. Interrupt output. Then let's say you type some character using your keyboard, and timer interrupt also happen at the same time. And CPU will process FIQ, timer interrupt first. This one is higher priority. Same thing happens, FIQ higher priority. So FIQ happens, then hardware will set I bit to 1, F bit to 1. So that means CPU will not take no interrupt, any interrupt, IRQ or FIQ. IRQ interrupt happens, CPU will set I bit to 1. So only normal interrupt, I bit to 1, F bit to 0, right? 0. It means only normal interrupt is blocked. If FIQ happens while you are processing normal interrupt, what if FIQ happens? Then that will be taken by CPU. So IRQ, ISR. What if in the middle of executing IRQ, ISR, then what if FIQ happens? Then that will be taken because F is also. Because it makes sense, right? FIQ has higher priority, right? So I don't want to wait. If FIQ happens, I can respond immediately. I'm not going to wait, right? That is the meaning. Right? And software interrupt. Okay, this one should be SVC, not SWI. So this one is, some old documentation from old documentation. So SVC, software interrupt happens, then what? I bit will be set 1, only I bit. Okay, so that is the meaning. So which bit will be set depending on interrupt or exception event. Okay, so reset. In case of reset, you turn on the machine, turn on your smartphone, turn on JetBoard. Then initially, all interrupt, normal interrupt, fast interrupt are blocked. Okay, CPU will not take because you have to do initialization. During initialization phase, I'm not going to take interrupt. I'm not ready. I'm doing initialization, right? I'm not ready. Right? That is the meaning. Okay, then returning from. Okay, so this one it should take some time. This one. Sujin. Hey, long time no see. Can you please? Can you see? Okay, done. Okay. When you return from exception, okay, we used what? In case of software interrupt, we used what? Move S, PC, LR. So you are returning back to the interrupted place, right? And S means SPSR will be copied to CPSR, right? Two operations, right? Copy this one and but in case of, so this one is a little bit nasty detail, but very important but nasty detail you must follow. Okay, Susan, can you please complete this one? Okay, thanks. In case of software interrupt, this one is making sense. You are copying LR to PC, but in case of IRQ, look at this, IRQ or FIQ, you have to do little change to link register. Okay, so this one is a little bit nasty, but very important rule you have to follow. Otherwise, it's not working properly. ARM CPU is not working properly. So in case of IRQ, ISR, normal interrupt, right? So IRQ, ISR, then when you return, you have to use this instruction, solve S, PC, link register, then number 4. So according to this table, the last row, like IRQ -4. That means what? You have to do your CPU is doing this operation. You see LR minus 4 subtraction, right? And destination is PC. You have S. So same. SPSR is copied to CPSR. So the question is why? What is this? Why do you have to do this modification? This one is we are not that happy, right? So link register is saved during this transition, right? Link register is already populated, is populated by hardware, and you are not doing that operation, right? So here, right? So link register is updated by hardware. Hardware is doing that operation. Okay, but when you return, before you return, you have to do little modification. Why do you think so? In case of IRQ. Any idea? What do you think so? John, what do you think? Pipelining, good point. Can you explain a little more detail? Pipeline, what? Okay, very excellent, very good guess. But before that, let me explain some background. Right? ARM was founded in 1980s, roughly 40 years ago, and ARM was founded as a CPU company for embedded systems, and that is embedded system. The computer system inside for that time, computer system inside the car, computer system inside the TV, refrigerator, microwave, you name it. That is embedded system. Computer is deeply inside that electronic gadget. So computer can be categorized into two: general purpose computer system. The other is embedded computer system. The computer you are using is general purpose. You can do anything you want. Right? And embedded system, specialized computer system. Embedded system. It is special purpose computer system. Think about computer inside TV, HDTV. That computer is responding to your remote controller. You are turning on and increase volume, decrease volume, right? Changing channels. Right? So computer inside TV is responding to your request. Only that purpose. And the important thing about embedded system, it is very sensitive to price. Right? Because it is very competitive. Embedded system is usually very competitive market. So CPU price is very sensitive metric. If the performance of CPU and function of CPU are similar, then cheaper CPU is more competitive, right? Customers want to purchase cheaper CPU. So cheaper CPU means what? Cheaper CPU means you want to use a small number of transistors. Small number of transistors to design CPU. Okay? Small number of transistors, small number of switches. That means cheaper CPU. Okay? So ARM was founded as that CPU company for embedded system. So their goal is how can I design a cheaper CPU, cheaper than other competitors. So they are thinking about that. You have to that premise in mind. Then think about a 5-stage pipeline you studied in computer architecture. Fetch, decoding, execution, memory access. Right? So let's say this is addition. Then subtraction. R4. R1, R2, okay. Then LW. R4. Okay, I'm cooking up just some code. So pipeline, the fetch, decoding, execution, memory access. Here, fetch, decoding, execution, memory access. So clock is running like this. Okay. Then let's say this instruction is located at 100. The next instruction is located at +4 position. This one, +4 position. So if you draw a PC program counter, drawing this step very carefully. Okay, that's program counter PC. So you are reading, CPU is reading this instruction located at 100. So 100. CPU read the instruction. If I draw instruction like this, instruction is coming in after little delay, from memory. So there is addition instruction. So CPU will get instruction doing decoding. And at this clock cycle, CPU is decoding addition instruction. At the same time, CPU is reading second instruction, which is the subtraction instruction. So here, program counter got changed to 108. And at this clock cycle, CPU is doing addition operation at this point in time, right? CPU is doing addition operation for this instruction. And at the same time, CPU is doing decoding, interpretation of subtraction. At the same time, CPU is doing what? Instruction fetch. Okay, from location 104, 108. Okay, and so on. And then let's assume that IRQ happen interrupt. You press the button. Okay, I press the button, then interrupt line direct. This one IRQ. Okay. Then what should happen? CPU should complete some instructions, right? CPU probably okay, I'm going to complete that instruction to the end. Okay, then CPU should resume from this instruction later on. So, right, so ARM architect decided to complete instruction which are in execution stage or better. Here you have memory access stage, the previous instruction, right? Execution stage, decoding stage, fetch stage. Execution stage or better, memory stage, wrapping stage. CPU architect decided to complete instructions which are in execution order. So that instruction will be finished. Okay. And CPU should resume from this place. Okay. When you return. When you return, right? You have to resume from the place, right? Addition instruction, subtraction instruction, resume. Right? But take a look at this. In the execution stage, program counter already got changed to 108. Program counter is pointing next location, not this location. Already got changed. Right? So ARM architect simply decided to store that program counter to link register. So second operation, right? Link register will be saved to return location, right? This one. That is what ARM architect decided to do. Okay? To save transistor. Probably, to make your life easier, because this is a really nasty, right? nasty aspect, right? So you have to do little modification. If hardware is doing some modification for you, hardware is doing subtraction, -4 for you. That means CPU should have adder. One adder. Then PC should be supplied here. Then -4. And that is, if that is saved in link register, you are happy, right? From software programmer point of view, right? I don't have to write this code, right? I can use just move, same move S instruction. This one. This one is more intuitive, right? And better from programmer point of view. But architect decided not to use this method to save, hardware cost, to reduce the hardware cost, right? To reduce number of transistors. Adder, right? That is a transistor, right? To create, chip CPU, chip for CPU. So that is the story behind. So because CPU is saving 108, when you return, you have to do -4. To return to this place. -4 is this one, -4, 104. Okay. Any question about this? So again, this one is a little nasty, detail. But we are not happy also. But you don't have any choice. You must follow that rule. Otherwise, CPU is not working, right? So depending on interrupt types or exception types, sometimes you have to do little modification to link register. Okay? When it comes to software interrupt, you don't have to do any modification. So SVC, right? You don't have to do any modification. But IRQ, FIQ, -4. You have to do that operation. That is why this code, right? Subtraction, depending on interrupt types, right? Exception types. Okay, then let's talk about nested interrupt. Nested. Silent. Any question, please? Everything is clear, or you don't have any clue? Either of these two, right? You don't have any clue, or everything is clear? Okay, let's talk about nested interrupt. We have some issue with the nested interrupt. We have a very similar. This one is very similar issue to nested function call. I'm not sure if I have explained the nested function call or not. But let me explain. Nested function call. So you have main, and this one is calling some function 0. Okay. So inside this function 0, you are calling function 1. And inside this function, you are calling function 2. So if I do execution flow, here, so here I use function 1, function 2. You are using BL instruction, branch with link, okay, to make a function called F0. Okay. Then you are supposed to return that. Then here, same thing. You use branch and link F function 1. Okay, and return that. Here, branch and link function 2. So that is a nested function code. In case of nested function code, we have some issue. What kind of issue? Branch and link. If you execute this code, then what is done by hardware? Two operations. First thing, program counter will be changed to this label. Okay? So you have instructions, right? the label is a function name, is the location of first instruction. Location of first instruction. That is the label, right? So that operation will be done. And second operation, link register will be saved with one return location. Let's say it is A, return location A. Two operations will be done by hardware. And the same thing happens here, right? Branch and link F1. So you are CPU will do PC update to execute the first instruction. Okay. Second, link register will be, let's say this one is B location. B. Same thing goes together, right? Now let's just start. And before you return, to return to this place, what instruction do you use? Move a PC LR to return to this place. Okay. Same thing goes to here, right? Here you are using move PC LR to return back. And think about this. You know, LR will be same PC, right? So LR contains D. So you are going to this place and execute it. Then what would happen if you execute this code? Link register contains D, not A. It is overwritten by this operation. So when you execute this code, then you are returning back to this place. To prevent that from happening, what do you have to do? You have to push a stack operation. Push, right? Push link register to stack. Right? Here, push LR, because LR will be, used, and pop somewhere, pop LR, push and pop. We have the same issue with nested interrupt processing. Executing, CPU is executing its main, then interrupt got generated. So you are executing ISR. Okay. Let's say SVC instruction. SVC. So here, then let's say you hit undefined instruction. Undefined. Then another ISR. It's ISR for SVC and ISR or exception service routine or undefined instruction. You are jumping to ISR. Okay, so that is one. Then the thing is, so during this transition time, hardware is doing that operation, right? Hardware is saving CP context, right? CPU context to SPSR. Okay, let's. Sorry about this. Let's say interrupt, just interrupt. Normal interrupt, IRQ, and another IRQ. This one, IRQ. Let's say this one is for keyboard. Keyboard IRQ. This one is for mouse. Mouse, IRQ, ISR. Okay. So two interrupt, nested interrupt happening. So CPSR will receive two SPSR, IRQ mode SPSR. You remember this map, right? You have SPSR register, dedicated SPSR register in each operating mode. Supervisor mode, you have SPSR. Okay. IRQ mode, you have SPSR IRQ. So CPSR information, that information will be saved in SPSR IRQ. Here, CPSR will be saved into SPSR, which is in IRQ mode. That IRQ is SPSR. And another interrupt happens here. Let's say you use CPS instruction, interrupt enable. Then I did. So you enable interrupt reception, right? Using CPS instruction while in this ISR code. Then another IRQ happens. Then same operation happens, right? SPSR IRQ will be saved. Right? So that register will be overwritten. Okay, so CPSR register will be written to SPSR. Same thing goes to here. SPSR IRQ will be overwritten, and link register also, okay, will be overwritten by that operation. So to prevent that from happening, you have to do what? You have to do push operation. Same push operation. You have to preserve SPSR and IRQ. Push these two into the stack. Okay. Push SPSR, push link register before you enable. Okay, because you are overwriting, right? Because you are overwriting. Before you enable interrupt IRQ, you have to push, right, these registers. And then at the end, you have to pop. Okay, before you return, push and pop operation. Okay. So two registers should be pushed. The first one is SPSR, right? Push SPSR, right? Push SPSR. Then push link register. These two should be executed, and pop operation, push and pop. And ARM is providing a shortcut instruction, okay? Because it is, I don't want to write this code, SPSR push. So one instruction is doing these two operations. Okay. This one, Kono? Juna? Okay, SRS instruction is a shortcut. Instead of using two push instructions, you can use SRS. That is pushing your animation. That is pushing SPSR, then link register, SPSR and link register to the stack. And you have addressing mode, right? Same addressing mode, full descending. Right? So pushing these two into the stack. And when you return, ARM is also providing this special instruction, okay? Return from exception. And that instruction is doing opposite operation. So bottom, okay? SPSR and link register will be saved. Okay? Will be loaded into CPSR and program counter. So instead of using push and pop, we can use SRS and return from exception instruction shortcut. Okay. Any question so far before showing you a demo? So let me show you one demo. So we are not ready to you are not ready to you are ready for IRQ interrupt. So instead, we are going to use SVC software interrupt instruction and undefined exception. Okay, so these two interrupt and exception nested case. Okay. So that is 5 minutes. You can here. So you can download which one. This one. Software interrupt and undefined exception example code. Okay. So I created this project and source summary. So here I created my own interrupt vector table. Okay. So second vector is for undefined instruction exception, and third one is for software interrupt. Okay. So offset 0, offset 4, offset 8. Okay. So I'm setting vector-based register and change processor state to supervisor mode and set up stack pointer and change processor state to 1B, which is undefined mode. So this one is undefined mode, right? In undefined mode, you have a stack pointer. So I want to initialize stack pointer too. So change operating mode to undefined mode and initialize stack pointer and change to user mode. Then here, look at this. Nope instruction, and I put some illegal instruction using that word. It's like a data, right? So I put on purpose. I put this, all ones, okay, FF, 8Fs. That is illegal instruction, undefined instruction. So CPU execute nope, then this one, then undefined exception. Okay, undefined exception, then CPU will execute this one, offset 4. There is undefined, CSD undefined here, CSD undefined, and inside this ISR exception handler, we have software interrupt instruction. So it is like a nested interrupt exception case. So you first generate the exception, undefined exception, like this one, undefined exception, and inside the exception handler, you have SVC, software interrupt. So it is nested processing, right? Let's go to this. Undefined. Okay, so we start at main, then set up VBAR register. Okay, VBAR to use our own interrupt vector table. Then change stack pointer setup, user mode. Then now to 5, then undefined, right? Undefined exception generated. So you jump to here, handler. So here I'm pushing what? Save return state, right? So I'm pushing SPSR and link register. SPSR link register, right? To the stack. Then here, SRS, then RFP pair, right? Save return state, then return from exception. Okay, full descending mode. Okay, so I'm using SRS, then store multiple instruction to save the CPU context. Okay, so for the operation. Now software interrupt generated, right? So that will jump to offset 8. So 5. Then software interrupt handler. I'm doing same operation, right? SPSR and link register push to the step. Then CPU context, push. Then simply LED, toggle, right? Push, toggle LED, turn on. Okay. Then a pop operation, return from exception. Then if I press F5, then what do you expect? It's supposed to go back to where? RFE, supposed to go back to undefined handler, right? So right below, right, we executed SVC, so supposed to execute this one. Okay. And press F5. Here. Okay. So first, exception handler. Right? So pop operation. What if I press F5? Return from exception. Then you are supposed to go back to this place, right below, right? So F5, this place. Nope. Okay. So you keep generating same undefined exception, software interrupt generation, and so on. Keep executing this. Okay, any question? Yes. Okay to switch what? Handler? Oh. I can hear you. I can hear you. SRS, change this, switch these two. What you're saying is switch this one to here, like this. This one to like this. What do you think? What if you do this? No, you cannot, right? Because RFE instruction, return from exception instruction is updating program counter. PC, right? So if you look at this, it is updating, right? RFE instruction is updating, right? This one from memory. You are loading SPSR to CPSR, then link register. Right? That information will be loaded into program counter. That means you are jumping back to interrupted location. So the second instruction will never get executed, right? That instruction never get executed because you are returning. Right? So this is the last instruction you have to use, okay, in ISR like this. So that is the last instruction you have to use. Okay. Okay. Any other questions? So one last thing. In IRQ, let's say IRQ interrupt generated, then here IRQ interrupt, right? Hardware interrupt, then IRQ, ISR, then hardware, right? Hardware will do this operation. CPSR I bit will be set to 1. That means inside interrupt service routine, CPU will not take interrupt. Hardware interrupt. What if you put SVC here? SVC instruction. Software interrupt instruction. That software interrupt will be taken or not taken? Not taken? Taken? Not taken? Taken. Taken. Not taken? Why not taken? because you block TPSR IBit1. No, it will be taken. Why? Because that IBit is blocking only hardware interrupt. Right? IRQ, CPU is IRQ. This interrupt, that interrupt will be blocked from internal world, right? Not software interrupt. Software interrupt will be taken, even though you block IBit1. Right? So think about that. What is the typical usage of software interrupt? Why do you want to use software interrupt? Typical usage in operating system. Context switching. No, not really. Software interrupt, right? What is the system call? System call is the one, right? You want to call, right? File open in C, right? File open, file close. Exit is a system call. You want some help from operating system, right? So if you follow the source code, okay, open, close, exit in Linux, you will eventually hit SVC. So some SVC instruction. Okay. So inside ISR, sometimes you want to call open, file, close, exit, right? It is not supposed to be blocked, right? Inside ISR, right? Sometimes you want to file open, file, close, and exit, right? So it should be taken SVC. Logically, think about that logically, right? So again, this IBit is only blocking interrupt from external world, IRQ, hardware interrupt, not software interrupt. Okay? Don't be confused. That is sometimes a little confusing. Right? Okay, any question before letting me go? Okay, that's it. See you next time. Okay. 그래도 원리는 IBit하고 FBit은 하드웨어 인터럽트, 파트에서 들어오는 인터럽트를 블락할 뿐이고, 얘는 내부 소프트웨어 인터럽트는 우리 프로그램에서 따는 거잖아요. 집어넣는 거예요. 그 내부 인터럽트를 블락하지 않아요. IBit 블락하는 없어서 그렇지. SVC는 블락이 안 돼. IBit과 FBit에 의해서 블락이 되는 게 아니야. 얘는 IRQ 인터럽트만 블락하는 거고, 얘는 FIQ 인터럽트만 똑같은 거. 링크 레지스터를 조정을 해줘야 돼.
저희가 익셉션, 디파인 익셉션 아니면 소프트웨어 인터럽트 같은 경우 저희가 이제 할 필요가 없죠. 거기서 항상 웬만하면 북부 S를 쓰니까 저희가 사실상 서브 S를 저희가 코드를 작성할 때 쓸 일은 별로 없는 건가요?
그러니까 그렇지. 여기 보면 우리가 룰에 보면 소프트웨어 인터럽트하고 Undefined의 경우는 링크 레지스터를 조정할 필요가 없다고 되어 있잖아요. 그냥 그것도 생각을 해보면 당연한 거예요. 왜냐하면 우리가 아까 그 경우는 파이프라인 걸었을 때 하드웨어 인터럽트의 경우는 우리가 그거잖아. 키보드가 움직이고 마우스 언제 발생할지 몰라. 진짜 내가 이거 눌렀는데 CPU 입장에서는 내가 언제 이걸 누를지 어떻게 알지? 하지만 SVC는 알아. 그렇잖아. 소프트웨어이기 때문에 실행하다가 파이프라인으로 들어오잖아. 그러니까 그거는 이렇게 깨끗하게 핸들이 가능한데 하드웨어 인터럽트의 경우는 저렇게 지저분하게 되는 거죠. 그래서 트랜지스터를 좀 적게 쓰면서 CPU를 설계하게 됐어요. 그러니까 싼 CPU를 만들죠.
서브 S 같은 경우에는 사실은 뭐 내부적으로는 되어 있는 거고 저희가 굳이 뭐 할 이유는
내부적으로
이미 처리를 할 때 무브 S가 아니고 서브 S가 공적으로 되어 있는 거고.
아니요, 자동적이 아니라 이름 뭐야?
저
데이?
김대희.
데이가 ISR을 짤 때 그걸 써야 되는 거야.
아,
넥스트.
제가 코드를 짧게 직접 써야 돼요.
당연하죠. 이걸 써야 돼. 이렇게 리턴할 때 보고 리턴하기 전에 리턴하기 위해서 이 코드를 넣어야 된다. 무브를 쓰면 안 된다. 무브에서 이걸 쓰면 안 된다.
제가 코드를 짤때
그럼 그 IRK의 경우는
이해했습니다.
그러니까 좀 프로그래머 입장에서는 지저분 이거 왜 이렇게 해주겠대? 그냥 나 이렇게 하고 싶은데 짜증이 나는 거지.
제가 이제 IRQ를 처리하는 서비스 루틴을 직접 짤 때 이거를 추가.
그렇지. IRQ 핸들러를 짤 때 이걸 좀 써주겠다.
알겠습니다.
enable IRQ를 다시 써주신 거는
요거?
똑같은 하드웨어 그거라서 인터럽트라서
그렇지. 여기서 저에서는 하드웨어 인터럽트가 똑같은 IRQ 인터럽트가 발생했다고 생각을 하는 거니까 요 IRQ. 그러니까 여기서 enable 왜냐하면 가는 중간에 인터럽트를 막아버리니까 인터럽트가 발생해도 처리 중에 ISR 처리 중에 인터럽트가 발생을 해도 CPU가 무시해버리잖아. 그거를 방지하기 위해서 이제 enable을 시켜야지. 나 인터럽트를 받을게. 처리 중이지만 인터럽트를 받을게.
왜냐면 두 번째 인터럽트가 하드웨어 그러니까 뭐 IRQ가 아니면 뭐 Undefined나 다른 제가 그런 거는 enable 주잖아요.
어떨 것 같아? 안 해도 됐어. 생각을 해보면 IRQ가 발생했어. 근데 CPU가 처리를 하다가 Undefined 내가 모르는 인스트럭션. 근데 아무것도 안 하면 어떻게 돼? 말이 안 되잖아. Undefined 인스트럭션이면 CPU가 인스트럭션 발표시켜야지. 그것도 로지컬하게 생각해봐. 논리적으로 아무것도 안 하면 뭐야? 해커가 바꿔놨는데 그냥 무시하고 실행하라고 그건 말이 안 돼. 이건 익셉션이 테이크인 거지. 처리가 해야 돼. 논리적으로 좀 생각을 해보면 그렇겠구나라고 이게 맥센스 하지.
보통 뭐 하드웨어 IRQ를 코드를 짤 때 보통의 경우에는 좀 enable IRQ를 쓰는 편이에요.
보통은 써. 왜냐하면 네스티드 인터럽트를 허용을 해야 하는 게 맞거든. 그렇잖아. 여러 개의 인터럽트가 동시에는 아니고 많이 발생할 수가 있어. 주변에. 왜냐하면 I/O 장치들이 되게 많기 때문에 키보드, 마우스, 뭐 와이파이, NFC 뭐 엄청나게 많은 I/O 장치들이 있기 때문에 내가 키보드 인터럽트를 서비스 처리 중이지만 중간에 또 인터럽트 발생할 수 있어. 근데 이제 조건이 다음 시간쯤에 얘기할 건데 우선순위가 높은 인터럽트. 현재 처리하는 그 인터럽트보다 키보드 인터럽트보다 더 우선순위가 높은 게 발생을 하면 그럴 때만
그럼 IRQ 내에서
우선순위를 이제 구현을 해줘야 돼. 그거를 이제 다음 시간쯤에 그게 되게 중요한 거고. I/O 장치 되게 많잖아. 그러면은 그 최악의 경우 동시에 발생한 것도 우선순위가 있어요. 나는 타이머부터 처리해줄게. 혹은 키보드 그 다음에 이렇게 우선순위를 정해야 될 거야. 그런 이슈가 있습니다. 그리고 처리 중이지만 인터넷 처리 중이지만 좀 더 우선순위가 높은 게 발생하고 그런 처리를 해야지. 하지만 우선순위가 낮은 거가 발생했다. 그럼 무시해요.
그러면 보통 저 enable을 써준다고 하면 굳이 왜 맨 처음에 만들 때 IRQ를
왜 그러냐면 이런 게 있지. 지금 인터럽트 IDS를 일로 세팅하면 여기서 인터럽트를 안 받는 거잖아. 근데 여기서 지금 우리가 해야 될 때 중간에 하드웨어가 해야 되는 일을 한 거고 이제 소프트웨어가 해야 될 게 있어. 왜냐하면 이 컨텍스트, 이 상태를 보존을 하고 있어야 다시 돌아왔을 때 그 상태에서부터 다시 프로그램을 시작을 해야 되는 거잖아요. 그 상태를 여기다가 푸시하기 전까지는 만약에 여기서 인터럽트가 있으니까 푸시도 안 했는데 또 인터럽트가 있어. 그러면 이 상태 세이브하기 전에 지금 발생하기 때문에 복구를 못 할 수가 있거든요. 그래서 푸시를 하고 그 다음에 이메일 이런 식으로 시퀀스 푸시하고 그 다음에 이메일 이제는 나 거의 인터럽트 걸려도 괜찮아. 이미 이 상태 다음에 세이브 해놨어. 하드웨어가 세이브하는 게 있고 소프트웨어가 세이브하는 게 있고 요거 하기 전까지는 이메일을 해놨고 이제
하나 더 있는데 그 벡터 테이블을 저희가 마음대로 정의할 수 있다고 하셨잖아요. 근데 저거 같이 V바에 펄을 더한 거를 업데이트하면 이쪽에 정해져 있는 거.
정해져 있는 거야. 룰이야. 그러니까 암 회사에서 암 아키텍트가 정하는 룰이기 때문에 그거에 맞춰서 우리가 프로그램을 짜는 거죠. 저 위치에다가 이 위치에다가 그 벡터 브랜치 인스트럭션을 넣어놔요.
근데 그러면은 벡터 테이블의 순서를 어떤
순서가
마음대로 정리할 수 있다는 게 어떤 의미인지.
그 메모리 안에 나만의 나의 인터럽트 벡터 테이블, 인터럽트 익셉션 벡터 테이블 8개 8개의 벡터 브랜치, 리셋, 브랜치, FIQ, IX. 요거를 내가 코드로 만들어서 그걸 사용하겠다고 할 수 있다는 거예요.
리셋이 굳이 맨 위치 아니어도
근데 맨 밑에 0번지 말인가?
여러 개가 있으면 리셋 여기 세 번째가
소프트웨어 브랜치, SVC, IX.
이거 순서를
바꿀 수 없어. 요 테이블 안에서는 이 옵셋 0, 4, 8, 10, 10. 요 순서는 정해져 있는 거예요. 이거 바꿀 수 없어. 근데 전체 위치, 이 위치 여기 있어도 되고 여기 있어도 되고 여기 있어도 되고 어느 메모리에 어디 있건 통째 테이블 어디 있건 상관없어요.
저는 만약에 아까 데모에서 질문인데요. 브랜치를 그러니까 여기 맨 위에 이거 스택을 저장하는데 이 두 개 위치가 다르잖아요.
요거?
그러니까 SVC 스택 탑하고 Undefined 스택 탑이 그게 다른데 그러면 이 R13이 오버라이드 되는 거 아니에요? 그러니까 오버라이트 되는 거 아닌가요? SP
R13?
네. 그러니까 LDR을 해가지고
R13는 지금 이거는 뭐냐면 SVC 모드의 R13이고
네.
얘는 Undefined 모드의 R13이잖아.
네.
그러니까 이걸 보면
네.
그러니까 Undefined 모드의 얘를 요거 그렇지?
예.
그리고 좀 아까 뭐 있었지? 슈퍼바이저 모드의
예,
요거.
슈퍼바이저.
요 얘와 얘를 이니셜라이즈 하려고 하는 거야.
그러면 이제 R13을 그럼 부르면 그 해당 모드에서 이제
그치?
바로 그냥 자동으로
그치?
전환해도 돼요?
동작 모드를 R13을 액세스하기 전에 여기
예.
보면 R13을 액세스하기 전에 이미 동작 모드를 바꿨잖아.
예.
슈퍼바이저 모드를 바꿨기 때문에 여기서 바뀐 R13 얘를 사용하는 거야.
R13이고 그럼 평상시에는 이제 그러면 그냥 원래 모드 그러니까 시스템 모드로 그러면
그건 모르지. 동작 모드 얘를 봐야 되는 거지. 이 M비트가 어떤지를 봐야 CPU가 이 9개 동작 모드 중 어디 있는지를 알아야 내가 얘를 액세스하는지 이걸 액세스하는지.
그럼 다 개별적인 거예요. 이렇게 그 레지스터는. 그러니까
그렇지. 물리적으로 따로따로 있는 거예요. 물리적으로. 그러니까 여기 하얀색으로 아무것도 채워지지 않은 거는 동작 모드에 상관없이 같이 공유하는
공유하고
거고.
있고.
다 공유하고 있는 똑같은 R0. 하지만 이런 것들은 다 따로따로 있는 거예요. 따로. 동작 모드 여기서는 FIQ다라고 하면 요 R0부터 R7은 요 똑같은 걸 사용하지만
네.
R8부터 요거는 따로 있는 거예요.
따로. 아, 그리고 마지막 질문으로 그 SVC 그 명령어에서 이미디어트는 정확히 뭐예요?
그거를 이용해서 우리가
그러니까 아까는 첫 데모에서는 SVC 컨스턴트가 10이었고 여기는
그치.
10이었는데
그러니까
차이가
우리가 그걸 갖고 그런 시스템 콜을 구현할 수가 있는 거지. 무슨 말이냐면 이제 SVC 만약에 10이다 그러면은 요거는 파일 오픈 이게 20이다 그러면은 그냥 예를 드는 거예요. 파일 클로즈다 요거는 30이면은 엑시스다 그렇게 구별을 할 수가 있는 거예요. 똑같은 소프트웨어 인터프지만 뒤에 오퍼랜드를 보고 내가 어떤 거를 구현할지 그거를
지정하는 거.
OS 만들 때 운영체제 만들 때 그걸 보고 이 함수를 따로따로 구현할 수가 있어요. 근데 그렇게 할 수도 있고 뭐 여러 방식이 있는데 어쨌든 이렇게 할 수도 있다는 거예요. 할 수도.
지금은 뭐 그렇게 딱 큰 의미는 없고. 그러니까
지금은
데모에서
그러니까 SVC 인스트럭션 뒤에 이 오퍼랜드가 의미는 없어요. 그러니까 이제 ISR에 가면 SVC ISR에 가면 이 머신 코드를 읽어갖고 얘를 빼낼 수가 있어요. 빼내고 뭐 10이면 나는 이거 20이면 나는 이거 프로그램을 맞을 수도 있고 그렇게 할 수도 있다는 거예요. 그러니까 지금 요거의 의미는 뭐 별로 없는 거예요. 우리 예제표 대해서. 오케이.
감사합니다.
얘 뭐야?
이민성.
민성?
예.
오케이. 그래 수고.
감사합니다.